Okay, in this video what we're going to look at is a mass spectrometer and the physics that apply to it and how to solve problems involving mass spectrometers. So a mass spectrometer is something you see a lot like in chemistry, like it's used for analysis. You take particles and you can inject them in and you can basically shoot them through a magnetic field and figure out the charge to mass ratio of what's in your sample. So you can use it to figure out like what's in the sample of unknown stuff you have, right? And so in physics, we use mass spectrometer problems a lot because there's a whole bunch of different physics involved that all come together in this one thing, right? So this isn't really what a mass spectrometer in chemistry looks like, right? It looks more something like this. But solving these problems involves a lot of physics, and it's a good way to like bring it all together, right? So if you remember, mass spectrometer problems are three basic parts that have three specific physics principles that apply. Solving them is really easy, right? So there's three parts to it. There's the accelerator part, there's the velocity selector part, and there's the chamber part where you actually separate them by mass. So we'll look at each one individually and talk about like what physics are happening in each part. So the first part is the accelerator. And so what's happening in the accelerator is most of the times when you have these problems, you have this like potential source, right? There's an EMF, like a battery hooked up right here, and you have these two plates and they're both connected to either side of this EMF. And what that does is it creates a potential difference between the plates, right? So in this case, if my battery looks like this plate is going to be positive and the other plate is going to be negative. And so if I have these two plates at a different potential, right, that sets up an electric field. And so that electric field is going to point this way, right? And so it's a real simplified version, right? But if I take a particle and like I leave it at rest, in that electric field, if it has a positive charge, that particle is going to accelerate in the direction of the electric field, right? For all this, I'm assuming positive charge. So this particle is going to take off from rest and it's going to go this way and it's going to head towards this little hole in the gap there, right? So instead of hitting the plate, there's a hole in the plate so that it can travel through to the next part. So solving this problem is just a conservation of energy problem. So when you set this up, this charge, right, inside this field, there's an electrical potential energy there. And that electrical potential energy is being converted into the kinetic energy of the particle, right? So I can write a conservation of energy equation. So my electrical potential energy is equal to the kinetic energy of the particle at the end, right? So the electrical potential energy would be the charge times the potential difference, and the kinetic energy is half mv squared. The charge started here, so it's going to accelerate across that whole potential difference, right? So I should put this. And it's going to end up with some velocity. So I can take this equation and I can solve for what I need. I mean, 90% of the time you're trying to figure out the velocity, right? So I can multiply my charge times my voltage, multiply by 2, divide the mass over, and I've square root and I've got the velocity, right? But you can solve for anything with that. But it's just a conservation of energy problem. Okay, so the second part is the velocity selector. And so the velocity selector does exactly what it says. It takes particles that come in and it splits them up, and it only lets through things that have a specific velocity that you want, okay? So if you imagine these particles taking off from rest, right, not every particle is going to be at rest. So some of them might have a forwards or a backwards velocity, right, because things aren't always at rest. So some of these things are going to come in maybe going faster or slower than they were, or they should be, I should say. So this part will filter out the things that aren't going the speed you want. And so what it does is there's opposing electric and magnetic forces that will cancel everything out. So in this case, I'm going to have my bottom plate positive, and I'll make my top plate negative. And so if I do that, there'll be an electric field between them, right? So another example of using an electric field. So if I just did that, these particles would come in, they're positive, so they would all get accelerated towards the top plate and nothing would ever make it over to my third chamber, right? So in order to cancel that out, what we do is we make a magnetic field, right? And so in this case, I'll make a magnetic field pointing from your perspective out of the page. So if I do this, if you use your right-hand rule, right, so from your perspective, these field lines are coming out of the page at you, right? So take your right-hand rule, fingers in the direction of the field, thumb in the direction of the particle, and so that magnetic force will point down to cancel out that electric force, right? So if you look at a free body diagram of it, I have an electric force pointing up from that electric field, and I have a Lorentz force pointing down from the magnetic field, right? And if I get this just right, these two will cancel each other out. So I can say the electric force is equal to the magnetic force. So if I plug in what I know for electric force and magnetic force, right, what the equations for those are, then I can solve. So we know that electric force from the field, it's equal to the electric field times the charge. And then for the Lorentz force, it's the charge times the velocity times the magnetic field, right? We don't need the sine theta because it's going perpendicular. So if you look at this, these two cancel out. And I get an equation that says velocity is equal to electric field over magnetic field, which is really cool because all that means is you can put any electric field, you don't have to know the mass, you don't have to know anything. All you need to know is the ratio of the electric field to the magnetic field, and you will only get particles that come through that have that canceling effect. They'll have exactly the velocity you need, right? And so this is really cool too because it shows up like in the speed of light. If you studied anything about how the speed of light, like why it's always constant and how it's like the ratio of the electric constant to the magnetic constant, it's really cool, right? So the velocity selector is basically saying this. You can adjust that electric field and that magnetic field to get things going the right speed. And so what's going to happen, these particles that have the right velocity will have this right ratio, and they'll go through, they won't accelerate up and down. So they'll just make it all the way through here to my third chamber. But anything that's going too fast, right? If it goes too fast, my magnetic force will be too large. And so those things too fast will get accelerated down and they'll hit the bottom plate. Or they'll crash into the wall over here. Anything that's going too slow, this magnetic force won't be big enough. And if it's not big enough, the electric force is too big. And so those are going to go this way. They're going to go upwards, and they're not going to make it, right? So this hole over here is designed just for the things that have the right velocity, that have no acceleration to hit and pass through. Okay, so the third part of this is the actual chamber that does the mass measurement. And so, for the last part, the velocity selector, that was a balanced forces problem. So for the chamber, this is a circular motion problem. So if you think about what's happening here, inside this chamber, I've got a magnetic field, and I'm going to draw mine coming, again, out of the page at you. So when this particle comes in, right, when it gets into like right here, what's going to happen is you have a Lorentz force, right? So it's got a velocity this way, and the field is pointing out of the page at you, right? So there's going to be a magnetic force. So that magnetic force kind of points like this, and that's going to change the trajectory of that particle. So now the particle is going to maybe go over here. But again, now it's moving this way, right? Field, velocity, force points down. So again, it's going to be here. So you can see what's going to happen. It's a circular motion problem. You have this thing that's moving, and it's got a force pointing perpendicular to it, and it's going to end up taking a path kind of like that, right? And I can't draw great, but it kind of looks like a semicircle. And so that path will have a radius, right? And so what you can do is you can say, oh, well, I can just measure this radius, and that'll tell me the mass, right? Because it's a circular motion problem. So if you remember circular motion, right? The net force of something going in a circle is going to be mv squared over r, right? And so I have to set that equal to what my forces are that are making it go in a circle. Well, in this case, the force making it go in a circle is the Lorentz force. So I'm going to set that equal to qvb, right? And so if you look at that, mv squared over r equals qvb. So now I have an equation that relates where this particle ends up over here, the radius, right, to its charge, its velocity, and its field, right? And so you can rearrange to solve for whatever. So normally the problems will ask what's the mass of the particle, right? So you could take r, multiply it over, divide the v squared, right? And you'll be left with mass because you know the velocity from the velocity selector, right? You did this. And you know the radius, right? Because you can measure it here. And you know the magnetic field because usually like that's given to you. And you know the charge of the particle, right? Or if you don't know the charge of the particle, something else you can figure out from this is the charge to mass ratio. So Q divided by M, you can figure that out too. So mass spectrometer problems, right? Pretty easy to solve if you remember like the specific physics principles that will apply to each part. So the first part is just conservation of energy problem, right? You're setting the electric potential of this charge when it's at rest equal to the kinetic when it accelerates through, right? And then the second part is a balanced forces problem where the electric force and the magnetic force are canceling each other out. And so the things that have this specific velocity, E divided by B, will make it through that part. And then the third part you have a chamber and it's a circular motion problem. So you have this particle that's moving in a circle and it's got a Lorentz force acting on it, making it move in that path, and you can solve for what the mass of the particle is. So there's problems that have, just the second and third part. A lot of problems just have the first and the third part, but they're their own separate things, right? And if you remember the physics principles that apply to each separate part, then solving them is pretty easy.